can implement matrix algebra in the solution of linear systems. We will see how we expand the concept of integral to variables, multiple variables, and see how we can use this to find areas, volumes, and solve other type of engineering problems. And we will see vector calculus, in particular, Green's theorem, Stokes' theorem, and the divergence theorem, and review the concepts of curl and divergence of a vector field, as well as conservative vector fields. And finally, we will see the concept of sequences, series, and the development of Taylor polynomials. So let's start with differential equations. Differential equations are typically a relationship between an independent variable, typically x time, and a dependent variable, typically y or x, as well as including one or more derivatives of the dependent variable with respect to the independent variable. Differential equations represent dynamic relationships, that is, quantities that typically change over time and therefore occur regularly in engineering problems. The order of a differential equation is determined by the highest derivative present in the equation. Differential equations are formed typically from observation of physical models. We have seen, for example, how acceleration, velocity, and distance are all related, and how you can set up, for example, the equation of an object in free fall, making use of a differential equation setup. To solve a differential equation, we will need to find the equation that satisfies it. So this means that we have to mathematically manipulate the equation so that we have a relationship between the independent and dependent variables. So if the equation can be arranged easily in the form of dy and dx is equal to a function of x, then we can solve this by simple integration by taking dx to this side and having the y is equal to the integral of f in dx as the solution, or let me change the
okay, microphone should be better now, is it? Okay, good. Another type of differential equation is one that is known as being separable. That is, we can separate the differential equation so that we have all the terms in x and all the terms in y that are separate from each other. Again, in this case, we can solve it fairly straightforward by simply rearranging the equation. So for example, we would have g in dy is equal to the integral of h in dx. So this is known as a separable differential equation. A homogeneous differential equation is one in which we have the same total degree in x and y for every single term involved in the equation. So this is a homogeneous differential equation of degree 1, since x, y, and x are all of the first order. To solve this type of differential equation, you need to perform a substitution. The substitution is to set y equal to vx, and differentiating, you would have dy is equal to v plus x dv in dx. We then have linear differential equations, which are in the form dy in dx plus py is equal to q, where the terms p and q can be either constants or functions of x. To solve this type of equation, you need to identify the integrating factor. The integrating factor is always defined as e to the power of the integral of p and dx, where p is this term here. And the solution for this type of differential equations will always be given by this equation: y times the integrating factor is equal to the integral of q times the integrating factor in dx. We then have the Bernoulli differential equations. Bernoulli differential equations are expressed in the form of dy in dx plus py is equal to q times y to the power of n, with n different from 0 or 1. If n were equal to 0, then we would have a differential equation of the first order. If n were equal to 1, we could simplify and perform separation of variables. So the way to solve a Bernoulli differential equation is, first of all, to divide all sides of the equation by y to the power of n. Then you perform the substitution that z is equal to 1 to the power of 1 minus n, and hence dz and dx will be equal to 1 minus n y to the power of negative n dy and dx, so that this equation simplifies once you've multiplied all the terms by 1 to the power of 1 minus n, so getting rid of this term. You have the equation which is reduced to a linear first order differential equation, which then can be solved by the integrating factor e to the power of the integral of p1 in dx, where this is the integrating factor to solve this equation here. Once you have solved the differential equation in terms of z, you need to convert back to y from this substitution that was used previously. So let's see how we can solve these differential equations that cover all the different forms that we have introduced. So let's start with the first one. This is solved by simple integration, where we take dx to the right-hand side, so that we have the integral of dy is equal to the integral of 3x squared minus 6x plus 5 in dx, which gives us that y is equal to x cubed minus 6x squared over 2 plus 5x. The second one is a separable differential equation. So we can separate the variables so that we take y plus 1 to the left-hand side and we take dx to the right-hand side, so that the solution is given by the integral of y plus 1 in dy is equal to the integral of 2x in dx. The left-hand side solves to 1/2 y squared plus y, and the right-hand side solves to x squared plus c. The next one is a a substitution form. So we have dy in dx is equal to x squared plus y squared over xy. So we can see that all the terms are order 2. This is order 2, this is order 2, and this is 1 plus 1, which is order 2. So the substitution we need to make is y is equal to vx, from which v is equal to y over x, and dy in dx is equal to v plus x dv in dx. So with this substitution, we have v plus x dv in dx is equal to x squared plus v squared x squared x times vx. Where this here is clearly dy in dx, and here we have y squared, and this is y. So the term on the right-hand side becomes, once we simplify x squared, we have 1 plus v squared over v. Now we take the v on the left-hand side to the right-hand side, so that we have x dv in dx is equal to v squared plus 1 over v minus v. Taking the common denominator, the right-hand side becomes 1 over v. So we now separate the two integration variables, so that on the left-hand side we have v in dv. On the right-hand side we have 1 over x in dx. Solving this gives us 1/2 v squared is equal to ln x plus c. Now, we have not finished, because we have reached a solution in terms of v, but our integration variable or our integration function was y. So we need to substitute y over x instead of v, so that the equation becomes 1/2 y over x squared is equal to ln x plus c, from which we have the final solution, which is y squared is equal to 2x squared ln x plus c. Then we have the next one, which is a differential equation of the first order. Which is x dy dx plus y is equal to x cubed. Now, the way it is written now doesn't appear to be a linear first order, but dividing everything by x gives us dy in dx plus y over x is equal to x squared. So you can see that it now has the shape of a differential equation of the first order, which is dy in dx plus plus p y is equal to q, where in our case we will have that p is equal to 1 over x and q is equal to x squared. We know that the integrating factor is always given by the exponential e p in dx, which in our case becomes e integral of 1 over x in dx, which solves to simply x. We also know that the solution of a differential equation of the first order is always given by y times integrating factor is equal to the integral of q times the integrating factor in dx. So for us, we have y times the integrating factor, which is x, is equal to the integral of q, which is x squared, times the integrating factor, which is x in dx. So this becomes x cubed. So solving gives us y x is equal to 1/4 x to the power of 4 plus c. And then we have the last example, which is the Bernoulli equation. So we have dy in dx plus y over x is equal to xy squared. So this again has the form of a Bernoulli equation, which is dy in dx plus p y is equal to q y to the power of n. So how do we solve Bernoulli's equation? the first step is to divide by y to the power of n. In our case, we have y squared. So we divide all terms by y squared so that the equation becomes 1 over y to the power of 2 dy and dx plus y over x y squared is equal to x y squared over y squared. So these two cancel out. This one cancels out. Then we perform the substitution. The substitution is to substitute z is equal to y to the power of 1 minus n. In our case, n is 2, so we need to substitute z is equal to 1 over y, or y to the power of negative 1. And we need to take dz in dx, which we know is equal to 1 minus n, 1 over y to the power of n dy in dx. So in our case, dz in dx is equal to negative 1 over y squared dy in dx. So we find with these two substitutions, dz in dx plus z over x is equal to x. Notice now that this equation here has the form of a linear differential equation of the first order, where we have dy in dx plus px plus q, where p is equal to 1 over x and q is equal to x. We can now solve it by means of the, these are negative signs, apologies. So we can solve this through the integrating factor, where the integrating factor is e to the power of the integral of p in dx, which is equal to e to the power of integral of negative 1 over x in dx, which becomes e to the power of negative ln x, which is equal to e to the power of ln x to the negative 1, which is equal to 1 over x. And the solution is y times the integrating factor, which is equal to the integral of q times the integrating factor in dx. So the solution is z over x is equal to negative x plus c. We can rearrange so that we are expressing the solution in terms of z is equal to cx minus x squared. And now we need to solve for y, having substituted z is equal to negative 1 over y. We need to replace in this equation so that we have 1 over y is equal to cx minus x squared, which we can then express in terms of y as 1 over cx minus x squared. Any questions on any of these worked examples? So as we have seen, the solution to differential equation contains an integration constant, which we typically indicate with the letter C. Now, most of the time, we can keep this solution simply by indicating the integration constant C. However, there is a class of problems that require an exact solution to the differential equation. This means that we need to define the exact value of the integration constant. To determine the value of the integration constant, we must know the value of the solution at a particular point. So for example, the velocity at t equals 10 seconds, or the value of the function y when x is equal to 3. So this defines what are known as the boundary conditions of the differential equations. Typically, the boundary condition are determined at the start, and this is why they take the name of initial conditions. So we need to find the value of a certain function when the independent variable is equal to 0. So for example, here we want to solve the first order differential equation. Y prime is equal to x squared plus 7x plus 3 over y squared when y is equal to 3 when x is equal to 0. So this is a separable differential equation where this term is written as dy and dx. So we take y to the left-hand side and we take dx to the right-hand side, so that we have the integral y squared in dy is equal to the integral of x squared plus 7x plus 3 in dx, which solves as 1/3 y cubed is equal to 1/3 x squared plus 7 over 2 x squared plus 3x plus c. So we now need to find the value of c when y at 0 is equal to 3. So this means that we need to replace x with 0 and y with 3. So we have 1/3 3 cubed is equal to 1/3 0 cubed plus 7 over 2 0 cubed plus 3 times 0 plus c. So all these terms are 0. This is 81 divided by 3, which is 27, from which we find that the value of the integration constant is c, giving us a solution, which you find here. So of all the possible solutions identified by the equation 1/3 y cubed is equal to 1/3 x cubed plus 7 over 2x squared plus 3x plus c, of all the possible solutions represented by the equation, the only one that we are interested in is the one for which the value of the function y when x is equal to 0 is equal to 3. And hence, we have this equation as the exact solution for our differential equation. Now we can also study differential equations in terms of qualitative solutions. So we may have equations that we do not know how to solve. So for example, if you have a differential equation of the form y prime is equal to x squared plus y squared plus 1, this form here is not directly integrable, is not separable, it's not substitution, it's not Bernoulli, and so on. So we do not know how we could solve this equation. Nevertheless, we can gain some insight into the behavior of the function. And this is done through what is known as stability analysis, or identifying the equilibrium solutions. Equilibrium solutions are those which reduce the equation to y equals to 0. This means that the solution y equals c is a constant solution of that differential equation. This then allows us to determine the stability of a solution. So we can say that the solution is stable if the function tends to that value as t or x tends to infinity. On the other hand, an equilibrium solution is going to be unstable if the function close to that equilibrium solution tends to get further away. So let's look at this worked example where we want to find the equilibrium solution associated with the differential equation y prime is equal to 2y times 4 minus yt. So we need to solve this equation for y prime is equal to 0. When y prime is equal to 0, the solution is 2y times 4 minus y is equal to 0. So this gives us two possible solutions. Solution 1, which is y equals 0, and solution 2, which is y is equal to 4. So when y is equal to either 0 or 4, y prime is equal to 0, which means we have yt is a constant. So representing this, we have this line, which is y equals 4, and this, which is clearly y equals 1. So studying the equilibrium solution, we will see that y equals to 4 is a stable solution, while y equal to 0 is an unstable solution, since when we are close to y equals 4, the function tends to go towards that value, while when we are close to y equals 0, the function tends to move away from that value. Okay, any questions on first order equations before we move on to the second order? No? Okay, let's continue. We move on to second order differential equations. Second order differential equations are those which have a form of a y double dot or double prime plus b y prime plus cy is equal to 0, and a, b, and c are constants. In this case, we have a second order differential equation, so we'll need to find two solutions, y1 and y2, neither of which is a constant multiple of the other, so that all solutions can be written in the form y is equal to c1 y1 plus c2 y2, where c1 and c2 are the integrations of constants of integration. To find the solution of this type of second order differential equation, we need to solve the characteristic equation given by the second order polynomial of the coefficients a, b, and c. Solving this second order polynomial will result in three possible solutions. A solution identified by having two different real roots, which is case 1. Case 2 is when we have two identical real roots. And finally, the third case occurs when the argument of the square root is negative, which gives us two distinct imaginary solutions. The form that the solution to the differential equation takes, in this case, is a combination of exponential and trigonometric terms. We can also have non-homogeneous equations. That is an equation which is not equal to 0, but it is equal to a certain function of x, which is often known as a forcing function. We know that the solution to the homogeneous equation is given by assuming two real roots as e to the power of r1x plus b times e to the power of r2x. And we know that this solution corresponds to this term here being equal to 0. However, we need to add a term here that takes care of this fx. So the complete solution the general solution will be given by the sum of a complementary function, which is the solution to the homogeneous equation, and an additional term, which is the particular integral, which is the solution to the external force or function f. The particular integral can be found by assuming the generic form of the function on the right-hand side, substituting it into the differential equation, and then solving for the coefficients. Examples of general forms of the forcing function are given in this table here. So let's look at these examples. So the first is y double prime minus y prime minus 6y is equal to 0. We have said that to solve second order differential equation, we need to solve the characteristic equation. The characteristic equation has coefficients 1, -1, -6. So the solution, the two roots come from solving r squared minus r minus 6 equal to 0, which can factorize into r minus 3 and r minus plus 2 equal to 0, giving us the two real and distinct roots. R1 is equal to -2, R2 is equal to 3, leading to the solution y is equal to C1 e to the power of -2t plus C2 e to the power of 3t. The second one is y double prime minus 6y plus 9y is equal to 0. And here we see that the characteristic equation has coefficients 1, -6, and 9. This factorizes as r minus 3 squared, giving two identical roots, r1 and 2, as 3. So the solution, when we have two identical real roots, is given by C1 e to the power of 3t plus C2t e to the power of 3t. And the last example is y double prime plus 2y prime plus 5y is equal to 0. And the characteristic equation in this case has coefficients 1, +2, and +5. To solve this, we have -2 plus minus the square root 4 minus 20 divided by 2, which solves as -1 plus minus 2i. And we know that the solution is given by C1e to the power of -t. So the real term of the complex number becomes the argument of the exponent times the cosine of 2t. So the imaginary component of the complex number becomes the argument of the trigonometric functions. So C1e -t cosine 2t plus C2 e to the power of -t sine 2t. And then we have one more, which is a homogeneous equation, sorry, non-homogeneous equation. Which is y double prime minus 3y prime plus 2y is equal to x squared. And I think this may also be an initial value or boundary condition. Yes, so we have the initial conditions that y of 0 is equal to 3/4 and y prime of 0 is equal to 5/2. So first step is to solve the homogeneous equation. That is y double prime minus 3y prime plus 2y is equal to 0. So the characteristic equation in this case will have coefficients 1, -3, 2, which factorizes to r minus 2 times r minus 1, giving the two solutions 1 and 2. So the complementary function, which is part of the general solution, is e to the power of t, sorry, C1 plus C2 e to the power of 2x. Now we need to find the solution to the particular integral. The particular integral will have the form of a polynomial, since on the right hand side we have a polynomial. So our particular integral will have the form ax squared plus bx plus c, from which y prime of the particular integral is equal to 2a plus b, and the second order derivative of the particular integral becomes 2a. So we now use these three terms, y prime, and y double prime, and we substitute into the original differential equation, so that we have 2a minus 3 2ax plus b plus 2ax squared plus bx plus c is equal to x squared. So here we have this term here, which is y double prime. This term here is y prime. This term here is y. So we can now match the corresponding coefficients. So the second order coefficient is 2a is equal to 1. The first order coefficient gives us 2b minus 6a is equal to 0. And the zero coefficient, the zero order coefficient gives us 2a minus 3b plus 2c equal to 0. So the first equation gives us a is equal to 1 over 2. The second gives us that b is equal to 3 over 2. And the third one, we find that c is equal to 7 over 4. So the solution of the particular integral is 1/2 x squared plus 3 over 2x plus 7 over 4. So our general solution now becomes y is equal to c1 ex plus c2 to the power of 2x plus 1/2 x squared plus 3 over 2x plus 7 over 4. Now we need to determine the values of the two integration constants, c1 and c2. To do this, we resort to the information that we have about the value of the solution y and y prime when x is equal to 0. So we know that when x is equal to 0, y is equal to 3 over 4. And when when x is equal to 0, y prime is equal to 5 over 2. So the first solution, or the first condition, gives us c1 plus c2 plus 7 over 4 is equal to 3 over 4. While the second condition gives us that c1 plus 2c2 plus 3 over 2 is equal to 5 over 2, where y prime is equal to c1 to the power of x plus 2c2 to the power of 2x plus x plus 3 over 2. So we now have a system of two equations with the two variables being c1 and c2, which gives us c1 is equal to -3 and c2 is equal to 2. So finally, we can write the exact solution to this differential equation as y is equal to -3 ex plus 2 plus 1/2 x squared plus 3 over 2x plus 7 over 4. So this here is the exact solution to this differential equation and these initial conditions. So the steps to take when you have a non-homogeneous differential equation is to first find the complementary function, then find the particular integral, combine the two, make sure that the solution of the particular integral does not also occur in the general solution. Otherwise, you have to multiply that solution by x or t, whatever your differentiation variable is. Once you have identified the general solution given by the sum of complementary function and particular integral, you insert the initial conditions or boundary conditions to obtain the exact particular solution. Okay, any questions on second order differential equations before we move on? No? Okay. So multivariable function essentially extend the concepts of a single variable function. So a multivariable function is a rule that assigns a real number to each ordered set of real numbers x, y, z, or how many variables you want to have in the domain of the function. So this function will have a domain D in which it is defined. So a multivariable function has the same domain as has the same concept of a domain as a single variable function. So we cannot have negative values of logarithms. We cannot have negative values under the square root. We cannot have denominators that are equal to 0 and so on. So the same principles that inform the domain and continuity of a single variable function are also applied to the domain of a multivariable function. Similarly, the concept and definition of limit is pretty much the same as that for a single variable function. So we can say that the limit of a multivariable function is equal to a certain value L if we can make our function as close to L as we want by making the point xy or xyz equal to, sufficiently close to the values A, B, and C. The difference, however, is that while for a single variable function, we can approach a certain point A, either from the left or from the right. In the case of a multivariable function, we can approach the pair AB from an infinite number of different directions. So for many functions, we can simply calculate the limit by simple substitutions. So if we have a function, we substitute the values to which the two variables x and y are approaching, and we find a value L, we determine that that is the limit. We may, however, encounter indeterminate forms such as 0 over 0 or infinity over infinity. These forms, when they occurred in the single variable function, we could solve by, for example, L'Hopital rule. L'Hopital rule cannot be applied to multivariable functions. So if we have an indeterminate form, that is, we do not know what happens to the function as the variables approach that pair of values a and b, we need to study the behavior of the function around that point. We've mentioned that we can approach that point, AB, from an infinite amount of directions. So you can see here that we have 8 directions, 8 possible directions, all approaching the point AB from a constant x value, from a constant y value, or random curves. So if we determine that the limit as we approach the point AB from 2 different paths converges to a different value, so let's say L1 and L2, and these 2 values are different, then the limit does not exist. However, if we try out a number of paths and they all converge to that value L, then we may begin to suspect that the limit does indeed exist and is indeed L. However, we are unable to prove this mathematically by approaching the pair AB from any possible path, since there are an infinite amount of paths. So to solve this, we have to use the squeeze theorem. The squeeze theorem tells us that we have a function g, which is greater, or rather we have our function f, which can be constrained between 2 functions g, one that is always greater and one that is always smaller. If the function g converges to that limit, then so will the function f. So this is the multivariable extension of the squeeze theorem for single variable functions. Now, when we have single variable functions, we introduce the concept of derivative. Derivatives are also applied to functions of multiple variables. However, we introduce the concept of partial derivative. Since now the function can change not only along x, but also along y, so we can have a change along both directions, the partial derivative represents the change that a function has along one direction while maintaining the other variable as constant. So in this case, we see here the definition of partial derivatives with respect to x and with respect to y. For functions of 2 variables, if we differentiate twice, we will not have 2 derivatives, but we will have 4 derivatives, since we can have what are known as mixed second order partial derivatives. That is, first we take the partial derivative with respect to one variable, and then we take the derivative with respect to the other variable while keeping the first one constant. we can also introduce the concept of directional derivative. That is a derivative which is associated with a specific direction identified by a unit vector. To determine a directional derivative, we introduce the concept of gradient. The gradient of a multivariable function is a vector valued function for which the components of are the partial derivatives. So the component of the gradient along x, along I, is the partial derivative along x. The component of the gradient along j is the partial derivative with respect to y, and the component of the gradient along k is the partial derivative along z. Similarly to what we did for single variable functions, we can study the critical points, that is, those points for which the partial derivatives are equal to 0. So for any point for which the partial derivative of f with respect to x and the partial derivative of f with respect to y are equal to 0, or the two partial derivatives are not defined, then we identify these combination or these pairs of points a and b as being critical points for the function. So let's try to find the critical points, all the critical points for the function x e to the power of 1 over x squared, and so on. So the function is f of xy is equal to x e 1/2 x squared minus 1/3 y cubed plus y. So we have to take the partial derivatives. So let's take the partial derivative of the function with respect to x. So this means that we differentiate with respect to x, and y is considered to be a constant. So we have e negative 1/2 x squared minus 1/3 y cubed plus y plus x times negative x e negative 1/2 over 1/2 x squared plus 1/3 y cubed plus y, which we can write as 1 minus x squared e to the power of negative 1/2 x squared plus 1/3 y cubed plus y. Then we take the partial derivative of f with respect to y. In this case, we see that x is considered as a constant, and we integrate only with respect to y. So this gives us 1 minus y squared times e to the power of 1/2 x squared plus 1/3 y cubed plus y. Now, let's see when these two partial derivatives are equal to 0. df in dx is equal to 0 only when x squared minus 1 is equal to 0. That is, x is equal to positive negative 1. The second partial derivative, df in dy, is equal to 0 only when y squared minus 1 is equal to 0, giving y is equal to plus minus 1. So critical points are those for which, oh, sorry, I missed an x here. So df in dy is also 0 when x is equal to 0. However, when x is equal to 0, the partial derivative of f with respect to x is not 0. So we discard this solution. So we have the critical points that are formed by the pairs of positive negative 1 for x and y. So we will have A as negative 1, negative 1, B as negative 1, 1, C as 1, 1, and D as 1, negative 1. So these are the 4 critical points associated with this function here. So similarly to what we did for functions of one variable, we want to understand what type of critical points these are. We saw that for functions of one variable, we can have maximum or minimum, and the maximum or minimum is either local or global. This also applies to functions of multiple variables. However, because of the nature of the multivariable functions, we have a third type of critical point, which is not a maximum, is not a minimum, but is known as a saddle point. So to determine the type of critical point, we need to perform what is known as the second derivatives test. The second derivatives test is based on determining the discriminant for a critical point. The discriminant is defined here as the product of the second order partial derivatives minus the square of the mixed second order partial derivatives. So if the discriminant is greater than 0 and the second order partial derivative with respect to x is greater than 0, then we will have a local minimum. If the discriminant is greater than 0, but the second order partial derivative with respect to x is negative, this identifies a maximum. If the discriminant is negative, then the function will have a saddle point. And finally, if the discriminant is equal to 0, then we cannot determine what type of critical point that is. So sometimes we may want to find the constrained critical points. That is, we want to find a set of values of x, y, and z which satisfies a certain condition So this introduces the concept of Lagrange multipliers. So to solve the constrained optimization, in this case is just one constraint, we have to solve a set of 4 or more equations to determine the values of x, y, and z and lambda, which is the Lagrange multiplier. Notice that this method only produces options, candidates for the extrema. So once you have found the solution to this simultaneous equations, so you have a set of x, y, z, and lambda, you need to determine and verify that the solution that you have found does in fact represent the desired optimal point. So let's look at these examples. So we want to find and classify the extrema, the critical points for the function x cubed minus 2y squared minus 2y to the power of 4 plus 3x squared y. So we take the partial derivative with respect to x, which gives us 3x squared plus 6xy. And we set this equal to 0. And then we take the partial derivative with respect to y, and we find that it is equal to negative 4y minus 8y plus 3x squared is equal to 0. So the first fx is equal to 0 when 3x x plus 2y is equal to 0. So this gives us x is equal to 0, and this gives us x is equal to negative 2y. So when x is equal to 0 or when x is equal to negative 2y, this equation here is equal to 0. Now let's look at what happens to the second derivative, fy equal to 0. Let's see what happens when x is equal to 0. When x is equal to 0, the partial derivative becomes negative 4y, negative 8y. Sorry, this is y cubed, sorry. Is equal to 0. So we can collect 4y, and we have 1 minus, sorry, plus 2y squared is equal to 0, which is true only when y is equal to 0. So this gives us the first critical point, 0, 0. Now let's look at what happens when x is equal to negative 2y. we have that the partial derivative is negative 4y minus 8y cubed plus 3 times negative 2y squared equal to 0. So this becomes negative 4y, negative 8y cubed, negative 6y squared is equal to 0. And this factorizes into negative 4y, 2y minus 1 times y minus 1. So now we have three possible solutions. Y equal to 0, y equal to 1/2, and y equal to 1. When y is equal to 0, then since we substituted x is equal to negative 2y, x is equal to 0. When y is equal to 1/2, x is equal to 1. And when when y is equal to 1, x is equal to negative 2. Sorry, this is oops, I got these two inverted. So when y is equal to 1/2, x is equal to negative 1. And when y is equal to 1, x is equal to negative 2. So this gives us point B, negative 1, 1/2, and point C, negative 2, 1. It also gives us point D, which is 0, 0, but we have already found the pair 0, 0 from the previous substitution. So now we have identified the three critical points A, B, and C. To determine their nature, we need to study the discriminant. So for the discriminant, we need to find first the second order derivative with respect to x, which is 6x plus 6y, and the second order derivative with respect to y, which is negative 4 minus 24y squared. The partial derivative fxy is equal to 6x. So now we have the discriminant at the point 0, 0. We know that the equation of the discriminant is fxx at 0, 0 times fyy at 0, 0 minus fxy at 0, 0 square. So the discriminant at 0, 0, fx is 0, fyy is negative 4, and the fxy is 0, so this gives us 0. At point negative 1, 1/2, this gives us negative 6, and at point negative 2, 1, this gives us 24. So, since this is positive, we need to find the value of the second order derivative at that point. So fxx when x is equal to -2 and y is equal to 1 is smaller than 0, from which we determine that the point -2, 1 is a maximum. The point -1, 1/2 is a saddle. And the point 0, 0, we do not know what it is since the discriminant is equal to 0, so undetermined. Sorry, this was 12. Okay, then the second one is to find the absolute extrema within a certain region. So we want to find the extrema of the function 5 plus 4x minus 2x squared plus 3y minus y squared in the region bounded by the lines y equals to 2, y equals to x, and y equals to -x. So we want to find the absolute extrema within this region. So the procedure is the same. We find the first order derivative with respect to x, which is 4 minus 4x. We find the first order derivative with respect to y, which is 3 minus 2y. We set these equal to 0, so that the first one gives us x is equal to 1, and the second one gives us x is equal to 3/2. So the first critical point that we find is 1, 3/2, which corresponds to this point here. So this is point A. Now we need to determine if there are any other critical points on the boundaries of our region. So along the line y equals to 2, or along the lines y equals x and y equals -x. So let's study first boundary 1. Boundary 1 is y equals to 2 with x constrained between -2 and 2. So our function now becomes x2, not xy. So this becomes 5 plus 4x minus 2x squared plus 3 times 2 minus 2 squared, giving us the function of only one variable as 7 plus 4x minus 2x squared. We take the first order derivative and we have 4 minus 4x. We set this equal to 0 and we find x equals 1 as a critical point. Then we see the value of the functions at the two boundaries, -2 and 2. So when x is equal to -2, the value of the function is -9. When x is equal to 2, the value of the function is 7. And when x is equal to 1, the value of the function is 9. Now we look at the boundary 2. When x is equal to y, and again, x is limited between 2 and 0. So now the function is xx, from which we have 5 plus 4x minus 2x squared plus 3x minus x squared, which becomes, let's call this h of x, 5 plus 7x minus 3x squared, and taking the first order derivative, 7 minus 6x equal to 0 gives us x is equal to 7/6 as a critical point. So now we take the values of the function at the extrema, so 0 and 2. So h of 0 is 5, h of 2 is 7, and h of 7/6 is equal to 9.08. Then we look at boundary 3. Boundary 3 is x is equal to -y, with x constrained between -2 and 0. We perform the same substitution. We find a new function, let's call this k of x, which is equal to 5 plus x minus 3x squared. The first order derivative is 1 minus 6x, which is 0 when x is equal to 1/6. However, what do we notice about this point? This point here is outside of our interval for x, which is negative values of x between 0 and 2. So we have no points corresponding to negative values of x, and we have already found the value of the function at the point 0 and at the point -2. So we can now look at all the functional values corresponding to the critical points. So the minimum value occurs when x and y are equal to -2. Here. While the maximum value occurs from what we can see here at this point here, when x is equal to 7/6 and y is also equal to 7/6. However, we need to compare it with the functional value at the critical point A. Substituting 1 and 3/2 into the equation for our function gives us that f of 1 and 3/2 is equal to 9.25. So this point here becomes our maximum, and the point -2, -2 is our minimum. So what did we do here? First of all, we identified any critical point inside the region. We identified point A. Then we studied the behavior along the boundary. So we identified any critical point along the boundary, for example, 1, 2, or 7, 6, 7/6. And then we took the functional values at the extrema, at the upper and lower limit of the boundaries. We then compare all the functional values at the critical point and the boundaries. So -9, 7, 9, 5, 7, 9.8, and so on. Thus determining which one is the local, or sorry, the absolute maximum, and which one is the absolute minimum within that region. One last example on Lagrange multipliers. So we have our temperature function, which is x squared plus 2x plus y squared. And the region is the ellipse defined by the equation x squared plus 4y squared equal to 24. We need to find the maximum and minimum values. So we take fx, the partial derivative of the temperature. Actually, let me call this tx, as 2x plus 2, and ty as 2y. The partial derivatives are equal to 0 only when x is equal to -1 and y is equal to 0. So we have the critical point A, -1, 0. So -1, 0 is this point here. So this is the first critical point. Now we need to find any critical point along the boundary of the function. So the function is, let's call it g of x, which is x squared plus 4y squared minus 24. So we take the partial derivatives and we have 2x and 8y as partial derivatives. So now we apply the Lagrange multipliers, tell us that delta t is equal to lambda delta g, from which we have the two equations. 2x plus 2 is equal to lambda times 2x, and 2y is equal to lambda 8y. So solving this set of equation gives us either y equal to 0 or y equal to, lambda equal to 1/4. So if y is equal to 0, then x is equal to plus minus the square root of 24. If lambda is equal to 1/4, then x is equal to -4/3, which gives us the value for y as -4/3 square plus 4y square minus 24 equal to 0, giving us y is equal to plus minus square root of 50/3. So we have now identified the 4 sets corresponding to square root of 24, 0, negative square root of 24, 0, -4/3 square root of 50/3, and -4/3 negative square root of 50/3. So we have 5 possible critical points: A, B, C, D, and E. To determine which one is the maximum, which one is the minimum, we substitute the pairs x, y into the equation of the temperature. So we find that the temperature at point A is equal to -1. The temperature at point B is 33.8. The temperature at point C is 14.2. The temperature at point D is 4.7. And the temperature at point D is 4.7. So comparing all these values, we see that A corresponds to the minimum temperature, while B gives us the maximum temperature. Okay, any questions?